A client sends a payment request, but the network connection drops before the server can send an acknowledgement back. The client application then retries the exact same request to ensure that the financial transaction actually reached the backend system. Without a mechanism for recognition, the payment server treats this retry as a second distinct instruction to charge the user money. To solve this, we implement the idempotency key header, which allows the server to uniquely identify every individual request regardless of retries. The client generates a universally unique identifier version 4 and attaches it to the request header before the very first network call. The client must store this key in local persistent storage so that it remains available even if the application crashes during processing. Upon receiving a request, the server immediately extracts the idempotency key and checks it against a high-speed key value store. Redis or Amazon DynamoDB are typical choices for this lookup because they provide the low latency required for real-time payment validation. If the key does not exist, the server creates a new record and marks the transaction status as processing to prevent duplicates. This record creation must be an atomic operation to ensure that two simultaneous requests with the same key do not both succeed. In the event of a race condition, the second request should receive a 409 conflict status code from the server. Once the key is locked, the server proceeds to call the external payment gateway to perform the actual movement of financial funds. After a successful charge, the server updates the database record with the full response body, including the transaction identifier and status.
If the client retries now, the server finds the existing key and immediately returns the cached response without calling the bank again. This mechanism guarantees that the user is only charged once, even if the network fails a dozen times during the communication cycle. We must also protect against key reuse with different data. If a client sends the same key with a different amount, it must fail. The server stores a cryptographic hash of the original request body alongside the idempotency key to verify that the payload has not changed. When a hash mismatch is detected, the server returns a 422 unprocessable entity response to signal a logic error. Idempotency keys should not be stored forever. A time-to-live policy between 24 and 72 hours is usually sufficient. Expiring keys prevents the database from growing indefinitely, which maintains high performance and keeps storage costs within reasonable limits for the business. If a transaction is fundamentally different, the client must generate a brand new key to ensure the server treats it as a new intent. If the initial processing fails due to a temporary server error, the server should allow retries with that same idempotency key. Status codes like 500 or 503 suggest that the client should attempt the request again using the same key. Clients should use an exponential backoff strategy when retrying to avoid overwhelming the server during a period of high traffic or failure. In a multi-node environment, a distributed lock ensures that only one application instance processes a specific idempotency key at any given time. Update the payment status and the idempotency record within a single database transaction to maintain absolute consistency between the two states.
While there is no single global standard, many modern payment gateways use the hyphenated title Idempotency key as the header name. Many modern application programming interface gateways provide built-in middleware to handle idempotency logic before the request even reaches your microservice. For mobile apps, persist the key to the device's secure storage to ensure it survives if the battery dies or the app is killed. The cached response must be deterministic. Always return the exact same headers and body that were generated during the first successful execution. Using idempotency keys in your logs makes it significantly easier for system analysts to trace a single logical transaction across multiple retries. Ensure that non-financial side effects, like sending a confirmation email, are also covered by the idempotency check to avoid spamming users. Remember that standard hypertext transfer protocol GET and PUT requests are idempotent by specification, whereas POST requests require this manual key implementation. Verify your implementation by injecting network delays and forced server crashes during the payment phase in a controlled staging environment. If a client sends a second request with the same key but different metadata, it may indicate a malicious attempt or a bug. Monitor the ratio of unique keys to total requests to identify clients with poor retry logic or potential network infrastructure issues. As your transaction volume grows, ensure your key store is sharded to prevent the idempotency check from becoming a central bottleneck. Never rely on client-side timestamps for expiration logic, because system clocks on user devices can be inaccurate or intentionally manipulated. If the server takes too long to process the request, the client might time out and retry before the first attempt is finished.
This is why the processing status lock is vital.
It forces the second request to wait or fail until the first one completes. Define your idempotency storage policies using infrastructure as code to ensure consistent time-to-live settings across development and production environments. Using high-entropy random strings for keys prevents attackers from guessing valid keys and intercepting cached financial response data. When integrating with legacy systems that do not support headers, you may need to include the idempotency key within the request body. Correct idempotency implementation involves unique key generation on the client side, atomic locking on the server, and robust response caching. By following these detailed technical steps, you transform a fragile payment process into a resilient system capable of handling real-world network chaos.